Here are our solutions to quiz number 1 for ECE 320, Electronics 1. The first problem is adding resistors in series and parallel. Kind of like the Sp22 calculator, it's actually really easy to do this, especially when you get to problem 2, complex numbers. To use it, again, it's got a stack, and when you add, subtract, multiply, and divide, you're operating on the stack. So first, if I have R is 1314, I want to add it to 300 ohms. In series, resistors add. I set up the stack, X and Y, add them. I get 1614 ohms. That's in parallel with 400. So in parallel, the inverse is add. Take the inverse, 400, inverse, add inverse. This is 320 ohms. In series with 200, they add. In parallel with 500, 500 inverse, add inverse, 255 ohms plus 100. Answer is 355.03 ohms. Now where the HPs really shine is with complex numbers. For example, with this one. Slide this over. If I have R is 1314, to input a complex number on the HPs, at least the HP 42, I do 1314, enter, negative 300, complex. So there's negative 1314 minus J300. And let's do display, fix 03. So there's this resistance in parallel with 400. In parallel, the inverse is add. So take the inverse, 400, inverse, add, inverse. This is 309 minus J15 ohms, plus J200, 0, enter 200, complex. There's your J200. In series, they add. In parallel with J500, in parallel, the inverse is add. So take the inverse, 0, enter 500, complex. Take its inverse, add them. Take the inverse. So this is 137 plus J196, plus 100 ohms, 237 plus J196. You can basically get to pick whatever calculator you want. You just need one that works. HPs work really, really well for complex numbers, so I highly recommend them. Your pick, though, just anything that works for you. Number 2, or number 3. Write the voltage node equations. Now here I've got 5 nodes. I need 5 equations for 5 unknowns. The first one's kind of a gimme. I know that this voltage right here is 10. So my first equation is V5 minus V1 is 10. Second equation. I can't write the node equation at V1 because I don't know what this current is. I can't write the node equation at V5. I don't know what that current is. But I can write the node equation at V2. That's the current left, up, right, and down. Have to add a 0. So current left is V2 minus V1 over 500. V2 minus V5 over R, minus 20 milliamps, plus V2 over 200. So there's your node equation at V2, and note that all the V2s are positive, everyone else is negative. Node equation at V3, current left, current down, current right add to 0. Current left is 20 milliamps, right here. Current down is V3 over 300. Current right is V3 minus V4 over 600. And if you use this pattern, at node 2, all the V2s are positive, everyone else is negative. At node 3, all the V3s are positive, everyone else is negative. And if you check the units, I've got amps plus amps plus amps plus amps. That works. Amps, amps, amps. Volts, volts, volts. The units have to be consistent. And at node 4, the current up, current left, current down equals 0. Current up is V4 minus V2 over 700. Current left is V4 minus V3 over 600. Current down is V4 over 400. Now I need one more equation. That's a supernode. One option is this pink line. Draw a supernode. Current out of that supernode's got to be 0. So the current out is V1 over 100 plus V2 over 200 plus V3 over 300 plus V4 over 400. So there's your fourth equation, or fifth equation. 5 equations, 5 unknowns. Current loops. With current loops, the current or the voltage drop around any closed path has to be 0. Start with the easy equations. I know right away that I2 minus I4 is 20 milliamps. That's my current source. I can go around loop I1. If I start right here, I get minus 10 plus R times I1 minus I2 plus 500 times the current left. 500 times I1 minus I3 equals 0. Around loop I2, I don't know this voltage, so I can't do I2. I can do I3. So 100 I3 plus 500 I3 minus I1 plus 200 I3 minus I4 equals 0. I'm back where I started. Loop I4 I can't do. I don't know the current source. Loop 5. 300 I5 minus I3 plus 600 I5 minus I2 plus 400 I5, I'm back where I started, equals 0. Now I need one more equation. That's a super loop. One option that works is this big outer loop. So if I do that with the big outer loop, that's going to give me, let's erase all this. Right here, 100 I3 minus 10, because they hit the minus sign, plus 700 I2 plus 400 I5 equals 0. I'm back where I started. So there's 5 equations for 5 unknowns. Problem 5 is phasor voltages. The frequency is 1 over the period. The period is 0 crossing to 0 crossing, or peak to peak. Pick your favorite period. I did peak to peak. So it's this time to this time. And this is 2 milliseconds each. So there's 2, 4, 6, 8, 10, 12, about 13.2-ish. 1 over the period is the frequency. So the frequency is 75.7 hertz. Not exact, it's hard to read it off the graph exactly, but right around there. The amplitude. Amplitudes are easy, that's the peak. So there's the amplitude of x, about 2.8 volts. Here's the amplitude of y, about 4.4 volts. The phase shift is delay. A cosine is a peak at t equals 0. If I delay it, that's my phase shift. So this is the delay. X has a delay of right around 4.5 milliseconds. So the phase shift is the percentage of a 4.5 millisecond delay when period is 13.2 milliseconds. And notice the milliseconds cancel. Is that percentage of 1 cycle. Percentage of 360 degrees, and that gives you 122 degrees. A delay is the negative phase shift. For the phase shift on y, the delay is 3.2 milliseconds. Change that to 3.2, calculate it, I get minus 87 degrees. And note that pictorially, polar form is more natural. In polar form, I can see the peak and the delay. That's also equal to sines and cosines, if you care. Again, polar, rectangular, pick your favorite. They're both equivalent. The last problem is if I have this circuit, find the output when the input is equal to 12 plus 13 sine of omega t. And omega is based upon your birth date. That has DC and AC analysis. If I start with DC, let's do DC in blue. At DC, the frequency is 0. The inductor is 0 ohms at DC. Capacitor is infinity, meaning ignore it, open circuit. I get voltage division. V2 is just 1314 over 1314 plus 250. That's the equation for voltage division times the input, 10.08 volts. That's the DC voltage at V2. Now let's do AC. Let's try to do AC. AC. For AC, the input is 13 sine omega t. Real part is cosine, minus j is sine. So the input is minus j13, meaning 13 sine. The inductor is j omega L. So the inductance becomes J657 ohms. Resistors don't change. The capacitor becomes 1 over J omega C minus J1522. Now, to figure out what the output is, I combine these two in parallel, which would be, well, let's do it on a calculator. Bringing back the old trusty HP calculator, I've got 14 ohms inverse. The frequency is 1314. Capacitor is 500 nanofarads, 500e negative 9. 1 over that, so this is minus J1522.07. Let's do 0, enter 1, complex, times, so there's my capacitor, minus J1522 ohms. In parallel, the inverses add, so there's the inverse of R, inverse of C, atom, take the inverse. So all this together is 752. I just lost my calculator. Minus J649. Change my preference. Keep on top. Okay. Keep it from going away from me. Okay, anyway, so there's these two in parallel. By voltage division, it's R1 over R1 plus R2. So let's hit enter twice. Creates two copies on the stack. Now add 250 plus J657. So 250, enter, 657, complex. Now I'm going to add these two together. I enter twice because here's the numerator, there's the denominator, take the ratio. All that times the input, and the input was minus J13. 0, enter, negative 13, complex, times, there's your output. What that means, I did something wrong, is the real part is the cosine, minus 8.43, 8.49. Complex part is sine, 9.70, or minus complex part is sine. So that is quiz number 1 for ECE 320.